Thank you for the invitation, Barbara and Jan. And also thank you to all the my French colleagues who have been welcoming me in this first week back in France. As you can see, there's a number of new affiliations here. The bottom line is that you can call me Jean-Paul again. So as Luis pointed out, we're going to move from the nanoscale of these beautiful pictures that were shown in the previous session to the largest scales. That's what I mean by the macroscope. We'll zoom out not only in scale, but also in numbers of earthquakes. And most of what I'll show today is the result of results that are published in this recent paper. And is a result of very hard work by Menandrin Meyer. He's a postdoc in Caltech. Also a very nice collaboration with my colleague Tom Heaton. But I'll also take the opportunity to thank the extremely hard work that has enabled this research, which is all these teams who have made available and have produced these earthquake source products, which are catalogs of, very large catalogs of earthquakes that have been processed by Ling Ye, who was a grad student of Thornley and since 2 years ago a postdoc with us in Caltech, Martin Vallée at IPGP, and Gavin Hayes at the USGS. So these are 3 different data sets that we will use in this study. And these products were also enabled by, well, the advent of global digital seismology. So we couldn't do this a few decades ago. Most of this talk will be about observations, and I will only mention dynamic rupture models in a very conceptual way. But before we get into that, this is some simulations that we're doing now, dynamic rupture simulations, to try to explain some of the features observed during the Kaikoura earthquake in New Zealand. An extremely complicated rupture that involved many, many faults. Here on the left, what we have there are some of the faults involved in the rupture highlighted in green, and the colored circles are our back projection results, showing a very complicated path of rupture jumping from one fault to the other. And we developed several dynamic rupture models in order to understand what does it take for a rupture to be able to jump from, well, first to break all these faults and to jump and to break them in the order they did according to our back projection results. And this is a nice work in collaboration with Alice Gabriel and her team in Munich. So we're now in a position where we can start doing these very large-scale dynamic rupture simulations very quickly, actually, after an earthquake happens. And we'll be soon in a position where there's going to be a very strong synergy between dynamic rupture modeling and source inversion and source imaging. We'll be able to put more physical constraints into the characterization of earthquake sources. But we're not there yet. Another thing I want to point out with this example is that part of our work as seismologists is to focus on those very big earthquakes that often are surprising in some way, in at least one way. And from those surprises are always opportunities to learn something new. But the talk today will be of a different flavor. Instead of looking at a single earthquake, we will look at hundreds earthquakes and try to see what are the common patterns and what are the statistical properties of earthquake sources that emerge from a global study of earthquakes. So to start, we are inferring, or seismologists are inferring from, for example, teleseismic data, properties of the source, and those properties range from the very coarse on the left to the very detailed on the right. Now, on the right, we have finite source inversions, where the aim is to describe or to infer the spatiotemporal distribution of the slip velocity on the fault during the earthquake. On the left, we have just a point source representation, where we try just to come up with the moment and the moment tensor orientation. And an intermediate product is the source time function, which is the way the moment rate evolves with time during the earthquake. As you move to the right, you're adding more pixels to your screen, but not all of them are actually informative. There's a lot of noise, there's a lot of blur in those images. So it is high definition, but low fidelity, actually. So there's a lot of uncertainties that involve those source inversions that involve many parameters. So it's somewhere in between these two end members that we will find a sweet spot where we'll be able to have information that is robust enough that we can extract statistical conclusions about the earthquake and have confidence on it. So we will be studying today moment rate functions of 100 earthquakes or so. So that's one way in which we're using a macroscope. So we're not going to look at point by point on the fault of sleep velocity, just a moment rate, which is an integrated, this is the integral of the sleep velocity over the whole fault during the rupture. In a second way, we're doing a macroscope is that we're zooming out and going to the global scale. So we're not looking at a single earthquake, but we're looking at more than 100 earthquakes. And this is enabled by these new catalogs that have emerged in recent years. I'll be emphasizing the one developed by Ling Ye, which is, and here I'll focus on the subduction earthquake. So there's there's more than 100 subduction earthquakes in her catalog that have magnitude larger than 7. What she does is a finite source inversion. From that finite source inversion, what we are considering is the most reliable part of the solution, which is are the source time functions. What is nice in using this sort of new databases is that they are consistently processed by the same team using the same quality checks, using the same method across all these earthquakes. This is just a sample of those moment rate functions. So magnitude 7 and above. All the big ones that you've heard of recently are there. And some of the questions that we'll be asking to these catalogs are, what are the common features of earthquakes? My colleague Menandrin Meyer, his initial main motivation was earthquake early warning. So he's part of the earthquake early warning project in Caltech. So one of the questions with him are, do small earthquakes and large earthquakes start in the same way? So this is a crucial question for earthquake early warning because in many algorithms or in many approaches, there's this implicit assumption that there's something different in the first few seconds that helps us tell that this earthquake is not a small one but a big one, and that helps us make an accelerated warning to the region. So is that true or not? And there's been debate about this question recently. Are earthquakes self-similar at all magnitudes or not? The self-similarity is a very ingrained concept in earthquake source seismology, and it's pretty well verified statistically for at least for small earthquakes, let's say magnitude 5 and below. So what happens to the large ones? So those are the common features, but how are they different from each other? In what sense are they different from each other? Is there really events that are unexpectedly different, freaks? And what do we learn from these differences and similarities? What do we learn about earthquake dynamics and about the physics of fault mechanics? So let me start with a statistical analysis of these source time functions. What we did here is we separate them into magnitude bins. So this figure shows you, the magnitudes that are involved in every bin. So there's 7 bins here. And for each bin, we took the 20 earthquakes with the 20 nearest magnitude to some target magnitude. So some of those bins are very well separated. Of course, as you go to larger magnitudes, there starts to be some more overlap between the bins. All right, for each bin, we can compute a median source time function. All right, so there's 20 source time functions there. We'll compute the median. Here's one example for one of those bins. There's 20 source time functions in black, and the orange is the median. And here, all those medians are plotted together for different magnitude bins. All right, so what is surprising here is the onset. They all start in the same way, and they all start linearly. So those two things are surprising. The linearity is very surprising because the self-similar classical model would predict a quadratic growth. All right, second interesting aspect. Let's now process these same source time functions in a slightly different way. Let's first normalize them, normalize their time scale by their individual duration. All right, and let's normalize their amplitude in such a way that they integrate to 1. So we normalize it to integrate to some moment. So time and amplitude of a source time function being already normalized, let's stack them. Let's compute the medians, again, in magnitude bins. And that's what's done in this figure, and we're plotting all those magnitude bins together. And what emerges there is that there's a sort of universal shape to all these earthquakes. Of course, any distribution will have a median, but what's surprising here is that the median is independent of magnitude. They all have a common shape. And that shape is pretty simple. It's a triangle. Very symmetrical. All right, so on average, all source time functions for earthquakes, we're talking about earthquakes larger than magnitude 7-ish, scale to a very simple quasi-triangular shape. How do we convince ourselves that this is robust? So I mentioned that we're looking at 3 different data sets. So I just showed you Ling-Ling-Ye's one. And here are source time functions from plotted together from the other 2 data sets also. So what's important to note here is that these 3 analyses, these 3 products are obtained with 3 very different methods. Okay, let's compare first Ling-Ling-Ye's with Gavin Hayes. Both are finite source inversions. Well, the 3 use teleseismic data, but the approaches are different. So these 2 source inversions, Ye's and Hayes, they use a very different parametrization of the source in the inverse problem. And these are basically 2 end members of how one can parameterize the source. One is a so-called nonlinear parametrization, and the other one is a linear parametrization. So one has some restrictions, has some assumptions about the shape of the slip velocity at each point on the fault. The other is more free, has more parameters, but also more uncertainties. So 2 end members of how seismologists do finite source inversion. And Martin Vallet's ones are very different. It's not source inversion, it's deconvolution. So it's a very complementary, almost orthogonal approach to the other 2. And well, we can stare at these source time functions, and we can see that some are very similar in some sense. We can always find some exceptions that are pretty different. But if we go to the statistical properties and we plot the 3 catalogs in the same way, again, we find that they all produce pretty much the same result, that the stack of all these source time functions are simple and independent of magnitude. All right, so that's about the commonalities, the median. What about the fluctuations of this moment rate with respect to the median? What we can do for each earthquake, we can fit some function to a moment rate and then compute the residual with respect to that fit. So that's the difference then. Blue is the difference between the black and the red curve. And we can do this for the 100 earthquakes. We can separate them in bins. And we're plotting here on the right for each magnitude bin just the residuals. They're normalizing, their time scale is normalized. Something that's surprising is that, oh, yes, important. What we're plotting on the right are not just the residuals. So the residuals normalized by the median source time function. So they are the ratios between this blue curve and the red curve. All right, the relative residuals. And what we see here is that their amplitude and distribution, again, is very similar across all the magnitude bins, meaning that the statistical properties of the fluctuations are also pretty scalable. And what's interesting is that basically we're able to describe a source time function as some common pattern, which is the y-fit function here, multiply by some noisy fluctuations. So the noise here is multiplicative. What else can we say? We can look at the statistical distribution of these residuals. And what's plotted on the right is the empirical cumulative distribution of the residuals. The red dash curve is the cumulative distribution for a Gaussian probability distribution. So basically, all of them have very close to Gaussian distributions with pretty much the same standard deviation. So there's many aspects that are magnitude independent, pretty universal, not only on the median, but also on the fluctuations above the median. One more interesting aspect, we can look at the spectrum of those residuals. You can ignore the two first plots. Let's focus on the last one. The last one is basically the temporal spectrum of those residuals. And the interesting point here is the slope at high frequencies of this residual spectrum. It has a slope of -1, so that means that this is like Brownian noise, 1 over f noise. Some implications of this are that we know that the small earthquakes do not behave like this. If the onset of the source time functions is linear and is the same for all magnitudes, this implies that sort of the scaling between time scale and moment is quadratic. But the classical scaling is one in which the seismic moment is proportional to the duration of the earthquake to the power 3 cubed. So somewhere in between the small earthquakes, the smaller than magnitude 5 years of 6-ish that behave more similarly, and the large earthquakes above magnitude 7 that we have analyzed here, somewhere there's a break in scaling. Can we see that in the duration versus moment data? Well, here's the data, some of the data we have about that. There's a collection of data here plotted in black for smaller and moderate magnitude earthquakes. And the Ling-Ling-Yes data set above magnitude 7 is plotted here in colors. And there's a hint of a break in slope in this duration versus seismic moment, a log-log plot. But well, it's not obvious. Okay, summary of the observed characteristics of the source time functions magnitude above 7. All the source time functions can be scaled down to a common quasi-triangular shape. The onsets are linear and they're the same for all earthquakes. The fluctuations are multiplicative, Gaussian, and Brownian. Now let's try to put this in the context of more classical models of rupture in seismology. I mentioned this before, the self-similar model. The most basic version of the self-similar model of earthquake rupture is a circular rupture. For a small earthquake, if it's far from any boundary on the fault, there's no reason for the earthquake to run in one particular direction. Rupture velocity can be isotropic, so that's where this assumption of circularity may come. If the stress drop is constant, if the rupture speed is also constant, this sort of models predict that the moment rate function should start as t squared. And what we see is just t. Now, what happens when an earthquake becomes very, very large? That's when the earthquake starts as a circular rupture, but eventually it will reach the top and bottom boundaries of the fault. It will saturate the seismogenic zone. And from there on, it can only grow to the sides. So here's an example from dynamic rupture simulations. So it starts as a circular crack, and then it has only the opportunity to keep running as two pulses. So those models of very large earthquakes do predict different behavior, much slower growth than quadratic. So that's a good thing. However, the subduction zone earthquakes that we have analyzed do not saturate the seismogenic zone at the short timescales at which we see the linear behavior. We can see this linear behavior starting in the first few seconds, 5, 10-second timescales. Those timescales, the rupture hasn't had the time to saturate yet the 200 kilometers of seismogenic zone in the subduction zone. So this is not a good explanation for that. We can make a more general discussion. Those circular and elongated ruptures are two end members, but moment rate is actually the product of two things. One is the growth of the rupture area, and the other is the growth of the average sleep, or the growth of the actively sleeping region, the pulse size, if you want, and the growth of the average sleep velocity within the pulse. Those two quantities can grow, for example, as power laws with two different exponents, alpha and beta. Our observation of a linear onset puts a constraint that the sum of those two exponents needs to have a very particular value. What is it? 2. But there is a trade-off between these two. So one can come up with different kinematic models that will satisfy this observation. So in order to constrain dynamic models, we will need additional observational constraints on this. Okay, but let's come back to this idea of elongated ruptures. You don't need to saturate the whole seismogenic zone, actually, to turn a rupture into a pulse that is somewhat elongated. I'm going to show you some results from dynamic earthquake cycle simulations that Junle ran some years ago. We're looking at a fault plane. The dark area is locked. The blue area is the uncoupled part of the fault. It's mostly creeping in the very blue part. And I'm going to show you here in the next slide some snapshots of sleep velocity. The colors indicate the logarithm of sleep velocity. We're seen 3 times during an earthquake. And this is an earthquake that broke just the bottom rim of the coupled patch. It doesn't break the whole thing. Why? Well, it stays there because it's somewhat channeled by the high stress concentration that is produced by the surrounding creep. I think we've seen this mentioned conceptually in some previous talks. So yes, these border regions between seismic and aseismic zones of a fault are regions where stress concentrate, where stresses can become very heterogeneous, and that's where these elongated ruptures can happen. And this is not just a dream of a modeler, it's something that we see, for example, in the Gorka earthquake. This is an earthquake that was pretty elongated and was confined in the deeper part of the seismogenic zone. All right, so let me conclude here that thanks to this fantastic data sets, we're now able to probe the statistical properties of earthquake sources. We're making surprising findings that go against some of the most classical rupture models that we're used to. So this opens a lot of questions, actually. What is the origin of these patterns? What dynamical models are consistent with this? What is next? So we are analyzing the strike-slip ruptures too, and it's more challenging because they have more uncertainties. and talking about uncertainties. Quantifying these uncertainties will become important as we move into higher order, trying to extract higher order information about earthquakes. Of course, trying to develop methods with which we can analyze across this transition of scaling. Where is this break of cell similarity happening, and how does it happening? And with the goal of developing dynamic or physical models that are consistent with these observations. All right, I want to end up with this fun slide here. We did produce for this paper, this figure on the right, which some of you, if you are a little older than me, you may know this album by the Joy Division. That's the figure on the left. What you may not know is that this is actually coming from scientific data. These are pulsar signals recorded by the Arecibo radio telescope in Puerto Rico, which inspired this graphic designer to do that album. And we were inspired by that album, so that's full loop on science and rock. The editor of Science didn't like that so much. He preferred little piglets for the cover. Thank you.